This video is about interfacing circuits. The goal is that we want to pass information between two devices, usually two different types of controllers, or we want to operate an actuator out of our microcontroller. And so we have different voltages and different current or power levels. So this slide here just kind of reviews the digital levels. So we have TTL, which stands for transistor logic, and it has a standard voltage level of 0 to 5 volts. So the maximum voltage a TTL device can handle is 5 volts. A lot of small controllers like the BeagleBone or the Raspberry Pi can actually only do 3.3 volts. And so if you look at this, we have the TTL voltage. A low is any voltage below 0.8 volts, and a high is any voltage above 2 volts. But again, the maximum is 5 volts for TTL logic. However, if we look at it like a PLC, typically PLCs have digital inputs and digital outputs that are running at 24 volts DC. And so if you look at those, a low is still kind of considered, basically below 1 volt, or just call it 0.8 volts like the TTL logic. However, a 1 or a high doesn't really go active until you're at least 7 volts, or somewhere around 7 volts, which is well above anything a 5 volt controller can output, is let alone something like a Raspberry Pi. So you can't wire those up directly and expect a 1 coming out of a microcontroller like Raspberry Pi or BeagleBone or anything of that level and wire it into like a PLC and tell it, oh, hey, this is a 1, because it won't even see it till it gets up to 7 volts. So we have to do something to adjust the voltage. So we're going to look at some different things. Now, first, let's just take a look at a switch. So with a switch here, we have what's referred to as an operator, and then it has a pole, and then it has what we call a normally open terminal or contact and normally closed contact. Now, depending on the switches, you might have multiple poles and throws, or you might have just one of each, or in this case we have one pole but we have 2 throws. So the normally open and the normally closed are 2 throws. So here you have the switch has off position. So in the off position, then it's actually making contact with the normally closed contact. So if you apply a voltage to the common, that voltage now is connected to the normally closed terminal. So when the switch is in the off position, you actually can have current flow to anything connected to this normally closed connection. But then when you flip the switch to on, now it causes the pole to move and force this lever down to make contact with the normally open. So the normally open is now closed in the on position. And so power current flows through the common over to the A connection in this case. Now, if we wanted to wire something like this switch up to a microcontroller, like an Arduino or some sort of 5 volt device, because I'm using 5 volts here, we can wire this up in one of 2 ways. We can use what's called a pull-up resistor. So here the pull-up resistor is connected to the 5 volts. And so when the switch is open, then you have a 5 volt or a 1 into your controller. Now, if this was a PLC, it would be the same thing. You would just have this up at 24 volts. All right, but the idea here is that you've got this wired up here, so it's a 1, but then when somebody closes the switch, it now becomes a 0 into your controller. Or we can wire it the flip side, we can put the switch up to 5 volts. And when you do that, you have to put in what's called a pull down resistor. Now, you might say, well, why do we really need that pull down resistor? And the reason for that is you have to actually have uh, an electrical connection to ground to pull that down, because if you don't have that, when this switch is open, there's noise, just electrical noise all around us, from cell phones and light fixtures and whatever. There's all kinds of noise, so you have to make sure that you have a connection here. Now, the other thing you have to be very careful here is what size pull down resistor do you choose? So if you look at this and you say, okay, well, I could just put a 1 ohm resistor, that would pull it down. But if you did that, now you would have 5 volts and a 1 ohm resistor. So when the switch is closed, you're going to have 1 amp here of current flowing through this resistor, which is just going to overheat that resistor and waste a lot of energy. If it's only a half watt resistor, then you're going to buy a new resistor pretty quick. It's going to burn out. But either that or you buy really big resistors, which cost a lot of money, and you're just going to waste a lot of electricity. So you want to choose a resistor for something like this that is going to pull it down, but you don't want to waste a lot of current. So in general, I would recommend somewhere around the area of, say, 10 kilo ohms for a 5 volt circuit here. You could say, well, let's use like 100K or 100 meg, but sometimes if you make those resistors too high, they don't do a good enough job of pulling the values down. They kind of slow down the current a little bit too much. So in general, something like this would probably, I would recommend like a 10K. I tend to, in the classroom, we actually have like hundreds of 8.2Ks, so a lot of times I'll grab those and use those because we just have so many, and 10Ks are used for so many different circuits that you tend to not have that many spare. Alright, so we're going to look at several different conversion options here. So here is a simple voltage divider thing. So this is, say, in this case here, we've got 24 volts. So let's say this is our PLC on the left side, and we just want to connect it to, say, a 5 volt logic on the output. Then we can just simply do voltage divider. And so in this case, I chose a 20K for resistor 1. And so we put 24 volts here, and I got a 4.7K here. That's going to give us about 4.5 volts, or a good solid 1 or a high out into, say, an Arduino or some sort of 5 volt logic device. Okay, so we're stepping it down. Very simple. If you're stepping down, very, very easy. And if you needed to step all the way down to 3.3, you would just have to adjust the values of the resistors. Now, again, you want to choose values of resistors that are not going to have outrageously large current draws. So you want to be up there, so at least the sum of these is at least 10K kind of area, 8.2K at the or above would be my recommendation, so that you don't waste a lot of electricity just in this switching circuit. So in this particular example, I actually calculated the current. The current is 972 microamps, or 0.972 milliamps. All right, now here's a step up type of circuit. And the idea here is that we're going to go from a low voltage 3.3 or 5 volt, depending on what our microcontroller is doing on the left, and we're going to say wire that directly into something like our PLC or any sort of device that needs powered at 24 volts. And we just want to send this input in here. So what we can choose here, a BJT transistor or a MOSFET, as we have in this case. So in this case we have a MOSFET. This is a 2N7000 MOSFET. And so we're going to power the drain of the MOSFET with 24 volts with a pull-up type resistor here. And then over here on this input, we're going to have a resistor here. Now, I've seen a lot of times where you don't have resistor in line, but you know, it doesn't hurt to put it in there. It just makes the circuit slightly more complicated, but you could put in a relatively small resistor here, because remember, the MOSFET has a high input impedance. And so if it has such a high input impedance, very little current's going to flow through it. However, if you're doing a MOSFET, you really need to also throw in a pull-down resistor connected to ground to ensure that the gate, which acts like a capacitor in a way of the MOSFET, when you turn the output to 0, then this MOSFET can then discharge and shut off your MOSFET. Okay. So you want to do that. You want to have this pull down, and again, this pull down here, because when this is a 1, then you're going to have current flowing through this resistor and then through the R1 resistor here. I guess I got a couple R1s here, but through this resistor here, and you don't want that current to be too large, right? You need to make sure that that current is relatively small. Otherwise, you may damage your controller. So the output of a controller, you always got to know what the output of that controller can handle. In general, if you're talking about something like a Raspberry Pi or BeagleBone or Arduino, you're talking 4 to 5 milliamps as a maximum for the output for one output. But if you're turning on multiple inputs and outputs, then there's also like a maximum for all of them that is maybe something like 20 milliamps or something. So you need to make sure that you keep your current well below so that you don't damage your controller. But in this case, we're using this MOSFET, so the current is the current end of the MOSFET is basically nothing. Now we could do this with a BJT, bipolar junction transistor. If you do that, again, you kind of have to watch the currents. You definitely would have to have a resistor here, usually at least 200 or 300 ohms, because remember, a BJT will have a drop of about 0.7 volts when it's on. So this resistor is going to have to drop the rest of that. And so if you're using a BJT, you got to pay more attention to your current and the values of resistors. So usually a 100 ohm in that case would be too small. But you don't put the pull down resistor with a BJT. You don't need it. Okay. Now in this case here we have a 10K resistor. So what that means is we're just making the output a 1 or a 0 so that we can drive a higher voltage circuit, but we're not driving a lot of power. Now you can also use the same type of setup here to draw with a lot of current. If you had a small, this would be like your load resistor. If you're just turning on some device, then this MOSFET, you would just wire in your load where R1 is and just activate the load. So if you just want to turn something on or off with your microcontroller, then this is a nice circuit here, and the this R1 listed up here is your load resistor, and it could maybe only be a few ohms or something, and then you could have a lot of current that would just flow from the 24 volts through the load, and then when the transistor is on, through here. But notice that if you're using this as a logic out, as I show in this slide, that the output is inverted. So you see here, I actually, put this text upside down to just indicate this. So when you put a 1 here, your transistor turns on, which means that the voltage here is below that 0.8 volts. And so therefore it's a logic 0 out. If you put a 0 in, then you have this pull up, pulling it up, and this is off, and so now you have a logic 1 out. All right, now this is a circuit that's called a bidirectional logic shifting, and there's a link right here to DigiKey where this image came from. You need to really go read this here, and they demonstrate the use of this. So I'm just going to do it very quickly. But this is a typical MOSFET here. But we've got it hooked up now in such a way that we're going to wire this to our low voltage device, and then we're just going to have like a pull-up resistor to our low voltage value. So if we're using a 3.3, then that would be 3.3. If we're using 5 volts, whatever this low voltage is. And then you have your high voltage, which your high voltage could be a 24 volt or could even be higher possibly. But before you pick your MOSFET here, you need to make sure that the MOSFET can handle whatever that highest voltage can be. But this is an interesting circuit here because it allows the device on the right, the high voltage device, to send data into the low voltage device, or the low voltage device can send data into the high voltage device, and you're just using a single transistor. Now again, if you come over and read this DigiKey, they do give you a slightly more complicated circuit with 4 transistors, which has a little bit of extra kind of safety in it and stuff. But this type of circuit with a single transistor will work to allow the data to go in both directions. So it's a very handy circuit. Now again, this here, we're just talking about sending ones and zeros from one device to the other. But remember, a 1 or a 0 technically is a voltage. So we get, different devices are going to run at different voltages. All right, so here's that 2N7000 that we had in the previous slide here. And so again, when you're trying to pick a transistor, whether it's a MOSFET or a BJT, you need to go read the data sheet and make sure that you check the voltages and that kind of stuff. So you see here, like the gate to source voltage on your MOSFET has a maximum voltage of 30 volts. Okay, so as long as you're working in the 24 volt region or whatever, something like this circuit here would be fine. Now in this case, they were actually using a BS170. I didn't look up that data sheet, but I already had this 2N7000 because I have lots of these ones sitting around. So, but anyhow, you always want to look at that. You also want to look at what is your maximum current. Okay, so the on-state drain current for this particular MOSFET can handle about 75 milliamperes. Okay, to get it on, or oops. All right, so that's for like a minimum on, to operate kind of as a switch in the, as the minimum is like 75. Okay, and that's with a gate, a source voltage of about 4.5 volts. So you're going to have about 4.5 volts, um, to get that. And then if your drain current, remember your drain current is going to be limited by this resistor here and the voltage. Okay, so you see here, right, we got 24 volts, and then, forget the transistor for a minute, just 24 volts divided by 10K is only going to give you 24 milliamperes. All right, so we're actually below that value there. So it depends on what your load is to that transistor, what ID could possibly be. But then the nice thing about this transistor, and MOSFETs in general, is they have very low impedance when they're in this on state. So what this is telling you is that when this thing is on at 75 milliamperes, then it's going to have a resistance drain to source of about 5.3 ohms. All right, and so therefore you can calculate how much power this thing's actually going to dissipate based on what the voltage is, what the current is, and then how much power. Now, this is drain to source, so you need to know what the drain to source voltage is for that particular circuit. So you would, but they're telling you that it's about 5 ohms resistance when this is in that on state, and so therefore you can easily calculate what the voltage drop would be based on your voltage and your load resistor. All right, so this is the schematic for the MOSFET here. This is actually a relatively low power one, okay, even though it can handle like half an amp. That's an awful lot of current to run through this little device. Okay, they definitely make these things much larger, and so when you look at the larger ones, they can handle, amps, many amps depending on how big it is, but they come in different packages. This package here, about half an amp is about it. But what I want to kind of point out to you here is the actual schematic. It wasn't shown on the other ones. Is this here, we have the MOSFET kind of on the left side in this circle, but then on the right side it actually has a diode. Okay, in this case it's actually apparently a Zener diode, but this diode, what this does is it allows freewheeling access to allow the, if you have an inductive load like a relay or an electric motor or something that you're driving with this, it allows that inductance to dump its charge without destroying your device. Okay, so this diode here is built in to this MOSFET, and a lot of these power MOSFET devices and just power switching devices will have these diodes built in automatically, but these diodes are there to allow the inductive load to discharge its stored energy without destroying the device. Because if you don't have a freewheeling diode and you have an inductive load, you can very, very quickly just destroy that entire device, and just the first time you use it, and you dump that load. All right, so op amps or operational amplifiers, these sometimes they require dual power supplies, and sometimes they don't. It depends on which ones you choose. Okay, but they have some very nice features. Number one, they have an extremely high input impedance. and they have a low output impedance, and they can have a very high gains. So we can use these as what's called a voltage follower type of circuit. And so this is a voltage follower type of circuit here. Now this one here, so this voltage follower circuit here just applies extra current to drive the transistor. So again, in this case, we have a BJT transistor, which needs a lot of current to drive it. So if you have a microcontroller that usually is not going to be able to supply too much current. So in this circuit, the op amp here is actually just runs off of 5 volts. Okay, it doesn't need a negative like some op amps. So some op amps can run off just a single 5-volt source. So this is an LT6203, and it can output about 200 milliamps. And so then depending on which transistor that you choose here and your load. So in this case, this is a 5 ohm resistor with a 12 volt source. So you're looking at 2.4, just slightly under 2.4 amperes of current would be flowing through here. So using the op amp does two things. It provides a certain amount of current. Now honestly, with this setup, I'm not sure this transistor is actually rated. I think this transistor is actually only rated for 1 amp of current. So I'm not quite sure about this circuit if it was tested or not. But the op amp is going to provide, like I say, several hundred milliamperes of current if you want to drive a BJT. And the input current, Vn over here, or well, the current coming in based on Vn, is going to be basically nothing at all. Okay, so if you have a microcontroller or whatever over here driving this op amp, you don't have to worry about any current in at all to activate that. The op amp is going to take care of the current to operate the transistor. So again, this is referred to as a voltage follower here because you're feeding back this voltage. So if you put a voltage of say 5 volts in here, then you're going to get 5 volts right here at V out. Okay, you might not get 5 volts at the base, but you're going to get 5 volts at V out. And so that would be a 1, and that's going to turn this on. But notice the current is coming through here. There's no current coming through the input, the negative input of the op amp. So all the current is being driven by this separate 12 volt supply. All right, another way of powering high current circuits and high voltage currents is to use a physical relay. So in this case, the physical relay is actually in its electromechanical switch. So what you have to do with your controller is you would power the coil of the relay, and that would energize the relay, closing these contacts. So up here we have a high power source. This could be literally several hundred volts here. Okay, it's a completely separate source, and in this case we're sharing a common ground, but you don't have to even share a common ground there. And so you can have this high power source completely isolated from your controller voltage. But we're going to close this switch, which energizes a relay, which pulls these contacts closed, which applies the voltage and therefore the current to your load. So electromechanical switches or relays are used for very, very high currents. Now they do have, since it's a coil here, it's an inductor, they do have that uh, energized. So if we're driving this with that microcontroller circuit, number one, it's going to take a certain amount of current simply to activate this. Nothing near like what's going to drive your load, but depending on the size of your relay, it could take several hundred milliamps all the way up to even an amp, depending on exactly how big this relay uh, is. It could take a significant amount of current to drive it, and then it's also storing that energy in the magnetic field. So when this dumps, you need to make sure that you have a freewheeling diode to allow it to dump. So like I say, it's going to take quite a bit of current to drive this, which means that you technically can't wire it directly up. So you're actually going to have to use one of them transistor circuits we just looked at to power the coil of this relay. So a lot of times you end up cascading these if you need a lot of power, a lot of current. Now, another thing that you can use is called an optocoupler. An optocoupler is pretty similar to the what we've already talked about, but the difference here is it uses to activate the transistor, instead of simply wiring it up with a resistor, you're going to activate it with a photodiode or possibly a separate transistor. But the difference here is you get 100% electrical isolation. So you don't have to worry about voltage spikes and things on the power end coming back into your controller and frying your controller. Okay, so that's the great advantage of an optocoupler. So here's just a picture of an optocoupler. You have on the left hand side is usually like an LED, and then the right hand side is what they call a phototransistor, where the base of the transistor is actually, instead of being activated by electrons, is being activated by infrared light. And so usually these things are fully enclosed in a package here so that light can't, in this case they're kind of showing this, oh well, these guys sort of built this one with a LED and a photoresistor that is just sensitive to light. But in general, these things are completely isolated. So you have here an infrared diode, and you put a positive on the anode of the diode, and you get current flowing through the diode. That gives you a 1, which therefore turns on the transistor and allows current to flow out the output. Okay. Now, the optocoupler, a lot of times these things are simply used for communications, as we've kind of shown here. So over here we have some sort of input coming from, again, it could be another microcontroller, and we're running it through here. Now this has got a 10K resistor here. I'm not sure, that seems like a little bit high of a resistor there. You would have to look at the specs for your particular optocoupler there, but that seems a little high for me for this type of setup. A lot of times you might not even need that for a communications level low current optocoupler. And so here we're just sending a voltage in and a voltage out to another controller, and we're not only are we able to maybe use different voltages on the input and output, most likely it could be different voltages, but more importantly is we have 100% electrical isolation between the two using the optocoupler. All right, so down here in this box, I actually talk about this R1 a little bit here. So for this particular case, I guess they're saying that we had that input LED to the optocoupler, Uh, we had 24 volts, and the data sheet said that it could handle zero point 0.1 amperes uh, into the optocoupler, which is actually a huge amount of current. So this is actually more of a power one. We got it hooked up to a microcontroller on the other side, but in reality, this actually could just be controlling a load in this case. But so the maximum current, if the maximum current is zero point 0.1 ampere, then that's going to give us a 240 ohms. Here it says 240 ohms is the maximum current. What they're saying is if you make R1 240 ohms, then it will give you maximum current. So that's a little confusing the way that was worded there. So in general, if this calculation, this was a maximum current to activate this thing, then you want to be below the maximum current. So I'm saying you should probably use a minimum of like a 330 ohm resistor for this particular setup, if this is the current, maximum current they're saying that they want. Now notice though, if the data sheet's saying that this thing can handle zero point 0.1 amps, what they're saying is that diode inside of there needs quite a bit of current. So if you try to feed it with 10 milliamps, that's not going to do it. Okay, so what we're saying here is if you just hook up like your Beagle Bone and try to power this optocoupler, you're not gonna do it. You're gonna end up damaging the Beagle Bone and not getting any communications out of it. All right, so here's just a slide. I found this here on electronic tutorials here, just showing the 4 different sort of setups for optocoupler circuits. And so you see here you have the diode to the transistor, or you have a diode to a Darlington transistor. So remember the setup of Darlingtons. You have one transistor, then powers a second transistor, and the advantage of that then is that you can actually not even double your current, but let's say that let's say you had a gain of 10 on each of these, so you would have your current from this first one, and then your current for the second one could be 10 times that. And so you get this multiplication factor of 10 times 10 would be like 100 current increase. They also make them for SCRs. Remember, SCRs are silicon controlled rectifiers, so those are diodes that you can turn on. And then they also have triacs. Now the difference here is SCR and these transistor ones up above here, these actually only allow current in one direction. Right, so these are NPN transistors, so that means the current's going to flow down into 5, pin 5, out pin 4. And so the current is only flowing top down through these. But this is a triac circuit here, and with the triac circuit, what that means is that current can flow in either direction. So once you activate the gate, current can flow down through 6 to 4, and then when the sine wave or the AC waveform flips, if you activate the gate again, it will allow current to flow from 4 to 6. So the triac one allows direction in both directions. But in these other ones, current can only flow in one direction. So these first 3 are for DC activation only, not AC. And if we actually go back and look at most of these other circuits, I didn't mention that, but this is a DC type of setup. Of course, it's just logic 0 to 1, so that's basically DC. Okay, so and this type of circuit here with the transistor, again, is you're just whether you're controlling a physical output over here, or you are trying to communicate between 2 different controllers either way, it's just DC. You're not going to have current flowing in the opposite direction, right? Current only flows through one direction here. Now, the relay that we just talked about, the load, you can apply AC to the load. Once you close these contacts, so the relay itself depends on the relay. Some relays are actually can be activated by AC. Um, some of them must be activated by DC. It depends on the design of the relay. But the load, whether the relay is activated DC or AC, the load can, through a relay, it's just a physical switch through these contacts. It can be AC or DC to the load. So here is just a circuit I found. I guess I didn't put the reference of this one here, but we have a Schmitt trigger connection here activating. So this on the left way, I don't show it, but could be a microcontroller or whatever, sending out a 1 or 0, a 0 to 5 volt TTL connection here, and we're running it through. So our maximum is 5 volts, and then I have a 1K resistor here, and I'm running this into my opto coupler switch here through the diode. And so, you know, the diode is going to take, say, about 1 volt, maybe actually a couple volts or whatever. But so it's basically saying here that we've got about a maximum of 4 milliamps flowing through this particular optocoupler. And it's just the bar is showing this 100% electrical isolation over to our power circuit. So here in the power circuit, then we're using the opto isolator to drive a BJT transistor that is then going to allow current to run through the motor. And so in this case, we're saying that we can have the base current is going to need, say, about 5 milliamps of current through here. So this R2, we're going to choose R2 in such a way that it's going to give us a maximum of whatever current we need. In this case, they're saying 5 milliamps. Now, again, we have to be careful that, you know, your connection here on the output side of your optocoupler is not a higher voltage or a higher current than what's needed. But remember, this is a transistor, so when this turns on, it will have a voltage drop across here. Usually it's going to be pretty small, probably less than a volt. But, you know, look at the data sheet for whichever optocoupler that you have and use those values to calculate what value of R2 here. In this case, it says 1K2. I think that 2 was supposed to be an omega for resistance. I'm not sure about any of these values on here. They're just kind of demonstrating. The motor here needed 40 milliamps to activate this 12 volt motor. And then here is that freewheeling diode. So this is a physically separate freewheeling diode connected in here to the circuit here, just in parallel with our motor. Okay, so if your transistor doesn't have that, now again, a lot of transistors will have this diode built in internally to the transistor. You have to look up the model of your transistor. This is a 2N3904 transistor. It definitely does not have a built-in diode, reverse bias diode. Okay, but some of the high power ones, or actually a lot of the high power ones, do have that diode built in here, so then you don't need to physically wire it externally. But you need to make sure anytime you're trying to design these circuits, you need to make sure that you have that freewheeling diode if you have any sort of inductive load. All right, so this is a solid state relay that we have in the classroom here. And so I put the data sheet in here for this one so you can review it. All right, so this device here, it has an input, so you can kind of see it in the picture up here. We have 3 is plus, 4 is minus. Remember, this is an infrared LED here, so you got to put a DC voltage on here to activate it. So it's 5 to 24 volts DC to activate it. Okay. It has a maximum impedance setting. They're saying you have a maximum of 7 milliamps through there. But notice they say see the note, and so I highlighted this spot here. So it actually can go up to a maximum. The one that we have in the classroom, I believe, is the one I highlighted here, can actually go up to a maximum of 15 milliamps. So again, you cannot power this directly through something like a BeagleBone or something that can only output 4 to 5 milliamps. Okay, even if it was at 7 milliamps, that would be too much. So to make this activate, you got to have, basically they're saying about a minimum of 7 milliamps for the one that we have in the classroom here. It looks like up to a maximum of about 15 milliamps through that LED. Okay, but you can connect to the load. So over here at the load, you can connect to the load. Now the one we have in the classroom is actually can handle AC. So it's actually the one we have in the classroom here is this one here that can go all the way up to 200 volts or 240 volts AC. So it's actually a triac in the load side. And so you can you activate this and it will allow it to run in both directions on the load. So you can actually run AC out of that. All right, but again, to activate this, you're going to need, somewhere along the lines of about 10 milliamps to activate that LED. All right, now here's an what they call a general purpose photocoupler, and this one here I just put in. You can see here, this one gives you 4. It's a integrated circuit. So it's actually got 4 optocouplers built in here. And when you connect this up, then you can actually have 4 separate circuits connected up here. So if you wanted to, send them to 4 different devices or however. But you want to read the data sheet. So this is not a power device here. This is just for isolation between for communications. Okay, but if you look at this, it can only handle 200 milliwatts. So it and the voltage. Collector and emitter voltage is actually higher than I thought it would be for this. It actually can go all the way up to 80 volts, but it's really designed for low voltage uses here, certainly low wattage. So a maximum of 50 milliamperes through each collector. So that's actually not too bad, but it's certainly not on the scale of some of these other devices. So you could maybe drive some smaller circuits like that motor circuit we just wanted 40 milliamps. So I guess we could drive that. We could drive 4 of those, I guess, with this particular one and still be within the ratings. Alright, so here we have a typical switching circuit with the transistor, again, kind of like the ones we looked at before, but here we have a BJT. So, the idea here is we have this GPIO connection from a Raspberry Pi or digital output, for whatever device this is, we need to know what the maximum voltage is. What is the voltage when this is a 1? So if this is a 1, then and we have a BJT, so if it's a silicon BJT, you're talking about a 0.7 volt drop here. So based on that, you want to choose this value of resistance such that your current doesn't exceed what your GPIO can output. Okay, so again, I would if you're using a Raspberry Pi or a BeagleBone sort of device, I would say make sure you don't go above 4 milliamps. And so you can choose this resistor to ensure that. And then you have this transistor, and based on that transistor, that will give you kind of a maximum of how much current this transistor can handle. So if you still need more current, then you would use this transistor to drive maybe another transistor circuit or a relay or something like that. In this case, on the left side, we just have the LED. So we're simply powering the LED. And so we need to limit the LED when this is when the GPIO is at a 0, then your transistor will be off, and therefore no current will flow through here, so the LED light would be off. When the GPIO pin goes to a high, to a 1, that's going to turn this transistor on and current's going to flow. So we want to make sure that this transistor hits saturation. So if the transistor is in saturation, then we'd be at, say, about 0.2 volts, maybe a little bit more depending on the transistor, but usually we use 0.2 volts for saturation between the collector and emitter. And so then we've got 5 volts here. Depending on the color of your LED, you're looking at a voltage on the LED somewhere between about 1.7 volts for red or green LED, 1.7, 1.8 volts. And then if it's a blue, it gets up a little higher to say about 2.1 volts or something like that. So depending on your LED and exactly how bright you want your LED to be, then you can calculate what the voltage drop must be across this resistor to limit, so based on the amount of current and based on the amount of voltage drop your LED is dropping, you can then pick this value of resistor. Now on the right circuit over here, this is a relay. So we've hooked up a relay, so we're going to use this transistor now to activate a relay, and then this relay here will have our common connection. We have a normally closed and a normally open on our relay. And so then we can drive a high power, again, depending on how big our relay, we could easily go up into the hundreds of volts over here on our relay and activate that. And then, but notice again, we have this freewheeling diode here, because anytime you have an inductive load, you better put in that freewheeling diode, or you're just going to be, buying new devices or new circuits and rebuilding the circuit, because it will blow immediately. All right, so I just had Grok do a summary here about what type of transistor do you want to use in this circuit here. Okay, so we could use the BJT as shown in there. It's current driven, so again, we need enough current to actually activate that device. Okay, so if we're going to drive it from the Raspberry Pi or BeagleBone, then it's going to need you may need an extra circuit to help drive it. The on state is if it's saturated, 0.2 volts up to higher voltages depending on how much current. So if you're going up to like a really high current, I told Grok to use like about a 5 amp load through the transistor, then your collector to emitter voltage can actually get much higher, and so and then you're dissipating a lot of power in that transistor. All right. For switching, BJTs are a little bit slow. They call it moderate here speed, with a slower tail, meaning it takes a little while to actually shut it off. So when you drive your controller pin to 0 to say turn off, it actually takes a little while to basically get that current off to 0. All right, but they're relatively simple and cheap to work, to use, but they only work at lower frequencies also, basically due to that tail, hard to shut them off. Okay. We have the power MOSFETs. Those were the first circuits we looked at. They are driven by a voltage. So 3.3 volts is sufficient to get a lot of them to work. Now, when you get to the higher power ones, you may still have to use some kind of circuit to up the voltage and then drive a higher one. So you may need an intermediate circuit. Just depends on how much current you need at your load side. Okay. In general, the power MOSFETs are going to dissipate less power than the BJT. So, usually you probably want to use a MOSFET. They're also better, faster at switching. Okay. So, if you have MOSFETs available, those are really probably the best way to go most of the time. There's also the insulated gate BJT. The insulated gate is kind of like a MOSFET. It has a gate instead of a base. I mean, it kind of has a base in there too, but we don't have direct access to that. We have a gate. And so the IGBT is kind of a cross between the two, because it allows you to drive more power. So IGBTs are ideal when you're doing extremely high power. So high voltages or medium to high voltages and very high current. Okay. So if you really need big power, then IGBT would be the way to go. But if you don't need big power, you could probably find a MOSFET, and that would be the way to go. All right, and here's just another table example from this one. Actually came from Wikipedia, and this one actually is given some voltages here. Now this one here is talking huge power. So they're talking about a power BJT that can handle voltages all the way up to 1,000 volts and currents up to 500 amps. So we are talking extremely huge loads here. All right, and then they just down here though, they just kind of tell us it's going to have a low input impedance, which means it needs a lot of current to drive it to make it work, and that's the catch on the BJTs. So you need a lot of input current, which is wasted energy, and again you need a driver circuit between your power BJT and your controller. So you need an extra circuit in there for sure. And it also has a low output impedance, so that's kind of nice when you're doing low output impedance. Means that you're not going to waste as much energy in the thing. So you are wasting energy at the input, but it's less energy at the output than the MOSFET. Okay, but again, it's kind of slow switching speeds. So if you need to switch really fast, then you don't want that. But if you're not worried about fast switching, that's not an issue. A lot of times, you're just you want to turn something on and leave it on for minutes or hours or whatever. You don't care about switching speed. All right, but if you're trying to do something like pulse width modulation to do variable frequency control of a motor, then you care about fast switching. So that's where you would go with the power MOSFET. So again, the power MOSFETs, um, the downside of the power MOSFET here is that it's going to have slightly higher output impedance, which means that maybe it's going to use a little bit more power than a BJT, but it has faster switching, okay, and it maybe is going to cost a little bit more. But we could power it with just a gate to source of somewhere between 3 to 10 volts. So we can power it fairly easily, but notice the current is a little bit less. So for 1,000 volt, a single power MOSFET maybe is only going to get us 200 amps instead of 500 amps out of the BJT. So that's where the insulated gate BJT comes in. So it's going to cost more than the other two, but it's going to give us higher voltage, higher current, okay, but a high input impedance, which means that we don't need such a high power circuit to power it. So it's a matter of looking at the options, knowing what's available, and picking the one that works for your particular needs.